Welcome to the next IRsweep webinar on the latest development on QCL frequency comms. My name is Andreas Hugi, and I'm happy to announce on the panel today Professor Jérôme Faist. So let's start right away with the agenda. I'll give you a short introduction on the IRsF1, the dual comms spectrometer that IRsweep is commercializing or selling. And on a second point, I'll give some application examples that we achieved with this IRsF1. Afterwards, Jérôme will take over and he will basically then do a more technical summary to explain the performances that we can that we see with this IRsF1. And at the end, we'll have a question and answer session that is open. So please post your questions inside the Q&A section. We will wrap them up at the end of the webinar. Let me start first with just a brief overview of mid-infrared and compare it to the near-infrared region for sensing methods. The QCL puts us in the fortunate position that we can work in the mid-infrared range. So compared to the near-infrared range, it means that you can actually access the fundamental row vibrational bands. And this gives a boost in terms of selectivity, specificity, and sensitivity compared to the near-infrared. The IRsF1 not only uses a QCL, but we actually use a frequency comm and in a so-called dual comm configuration. And not only do we have this advantage to work in the mid-infrared, we also have some very unique points that this dual comm spectrometer actually sets it apart from other spectrometer system. First of all, it's very fast. So you can measure fast processes. You can have high throughput measurements, for example. It's high resolution, which allows you to measure small molecules and avoid interferences. It's parallel multi-wavelength, which basically then allows you to measure complex mixtures and processes. And it's high brightness, which allows you to measure optically thick and real-life samples. So what does this mean? Well, high speed means we have microsecond time resolution. Here we see time-resolved kinetic measurement of a bacterial rhodopsin measurement recorded over 15 milliseconds of time. In this time-resolved mode, we can have microsecond time resolution with up to hundreds to about 150 millisecond integration total time. And it gives you basically an insight into the kinetic pathways of your chemical reactions. But the speed not only gives you advantage to see new kind of spectroscopy, it also gives you an advantage when you talk of signal to noise, because you have then basically the opportunity to average your signal over a long time. So even if your experiments are in the millisecond or second range, you will actually profit from a better signal to noise ratio if you compare, for example, to a FTIR and you get about 100 times better signal to noise ratio. So compared, we benchmarked here a Vertex 70 against the IRsF1. Now the signal to noise is of course also driven by the high brightness source. So we have a laser source, and if you compare it to traditional FTIR instrumentation, we have orders of magnitude higher brightness. This brightness is a direct consequence of, again, using a laser. And the laser then basically also allows you to have high resolution spectroscopy and to measure small molecules. Here you see a methane spectrum, a zoom in, and you see that we can, by actually sweeping the QCL comm, we can then basically resolve very narrow lines in such spectroscopy applications. And last but not least, the frequency comm actually emits over 60 to 100 wave numbers. So you have basically all this, this optical information in parallel. And this makes it very similar to an FTIR in terms of acquisition, in terms of how you actually acquire your spectrum. So the IRsF1 is really a complete dual comm spectrometer. You see it on the top left. You see the optical box. It is it is inspired by FTIR spectroscopy, and it is delivered together with drive electronics that you see there in the rack, and also software to actually drive the system and to convert the multi-heterodyne signal into a spectroscopy system. Furthermore, we have bandwidths of 60 to 100 wave numbers, and that's of course not what you get from an FTIR. But to compensate this, we have actually engineered exchangeable laser modules, which allows you to really select your target wavelength that you're interested in, and then measure. This change of laser takes you about 30 seconds or maybe 1 minute, and you're again measuring in the next experiment. I would say in 30 minutes, you can do your next experiment. Application-wise, we're keeping expanding. So we started with protein dynamics, which was basically folding and unfolding of proteins and peptides, which then was soon extended to combustion diagnostics. We do a lot of stop flow these days. We have customers doing spectroelectrochemistry, Professor Ian Burgess, for example. We have photocatalysis, photochemistry. I'll show some example on photophysics. And we have heterogeneous catalysis, TRVS, time-resolved vibrational spectroscopy, VCD, we have done some experiments, electrochromism, polymer chemistry is important, and high-resolution spectroscopy, including breath and trace gas analysis. So let's have a look at the high-resolution spectroscopy. Here you see basically the latest improvement that we have developed together with Muriel Lepere from University of Namur. We developed a high-resolution instrument, and basically what the main improvement compared to the system before is to have a very high resolution with an accurate frequency axis. On the bottom right, you see the instrument which was delivered to University of Namur, and it has been delivered a few weeks ago, I think 2 weeks ago, and the system is already up and running, and they're measuring their first high-resolution spectra. So here you see a methane spectrum that we measured together with them with a resolution of 0.0002 wave number over 60 wave number coverage. This measurement was taken in 5 minutes acquisition time. And if we then basically zoom in, so this measurement was taken a bit with smaller steps, but you can see that we can really reach those 0.0002 wave number resolution. This work was inspired or based on the work which was done by Lukas Emmenecker at EMPA in the ComTrace project that we're together in ATH and IRsweep and Uni-Neuchâtel, where they actually developed a high-resolution instrument with the goal of sweeping the laser fast. So they reach now timescales of 10 milliseconds to actually record the full spectra. But what they sacrifice is this perfect frequency axis, which was important for the research for Muriel Lepere. The next experiment, which I would like to actually show, is a collaboration with UC Boulder in the Mitchell group and together with Dr. Paul Drawn. And it's a photophysics experiment. The reason why I chose to show this specific experiment, there's twofold reason. First of all, it comes hot out of the oven. It has been done basically last week, and new measurements are always exciting. So this is the first time that we show those. And second of all, it is exciting because it really shows the capability of this instrument in terms of signal to noise that you can accept if you do time resolved time resolved measurements. So the experiment here is basically to excite a triplet state of an imidazole derivative. So you photoexcite it, and then you flip the spin of one electron, and you don't have an electron pair anymore, and you cannot occupy the same orbital, and basically the electron is excited in the next orbital. And this is a process which is a high energy process compared to the ground state. And this gives many interesting applications. One could be, for example, it could be useful for energy harvesting in for solar energy. Usually this is done in phosphorescence, but many molecules actually don't emit light. So the infrared absorption technique actually allows you to characterize that in a more broad sense. The experiment is shown here on the left. So we have a neodyne-YAG laser, which excites the sample at 532 nanometer with a 6 nanosecond pulse. And on top of the sample, we overlap also our probe beam from the IRsF1 at 1240 and 1300 wave numbers. And basically, we then trigger the system to be in sync with the pulse of the laser. And on the right side, you see those time-resolved measurements that we acquired. And you see basically, even at with integration times of 1 microsecond, you can clearly see that you have a bleaching of the ground state, and you have about three excited states which show up at 1255, 1240, and 1210. What is remarkable in this measurement is really the noise level. I mean, we're talking here of signals of a few milli OD, and the noise level that we reach here is really in the micro OD noise or even lower. The instrument gains more and more traction in combustion. We just last week we had 2 publications, which one was basically published and the other one was accepted. So the first one is the monitoring of formaldehyde formation in the shock tube. This was done in collaboration with Christoph Scholz. And what you see on the right side, top right side, is basically how you can monitor the formation and the composition of formaldehyde depending on temperature. So that is extremely exciting research and very valuable given the importance of formaldehyde for many chemical and combustion processes. Furthermore, Professor Ron Hansen has a manuscript which was accepted just also last week on dual-com measurement or dual-com results on high temperature reaction kinetics. They basically developed a fitting algorithm or a fitting procedure which allows them to extract methane, mole fraction, and gas temperature at different basically during the combustion. And they use this to see to track the temperature and methane time history evolution during a pyrolysis of isooctane. The laser development is always one of the most important, or it's a core activity that we do here at IRsweep to enable as many applications as possible. And I'm happy to announce each time that I have a webinar a new wavelength. So we have a new wavelength. It's at 1350 wave numbers, and the list keeps growing. So the important point here that I want to make is, if you see applications that you think the IRIS could be used for, please contact us, because the laser development is done according to customer needs. And so we do steer our laser development according to the phone calls we get or do. So, and we can also inform you about lead times that you can expect. To summarize a bit the key performance metrics of the IRsF1. So in terms of speed, we reached 250 nanosecond in this time resolved mode. Then in the high resolution mode, you can get up to 10 millisecond time resolution. The resolution you can get is below 10 to the power of -3 wave numbers with an accurate frequency axis. And if you're willing to sacrifice that, you can go even lower. Basically, when you go for a tuning of about 10 milliseconds, there's the resolution that has been shown is lower than 10 to the power of -5 wave numbers. Noise properties are excellent. We get milli-OD noise levels in 100 microsecond integration time over a spectral coverage of 60 wave numbers per exchangeable laser module. Now, the 60 wave numbers depends on the laser. We have now also already dual COM modules which go up to 100 wave numbers. And this is basically really development of the laser technology, and it's an ongoing process. And I'm sure Jérôme can also elaborate a bit on this on his part. With this, I would like to actually hand over the talk to Jérôme Faist. I think he needs actually almost no introduction because he's an icon in his field. I think one of his most important career step is that he joined the Bell Laboratories in 1991 in the group of Federico Capasso, where he had a crucial role in the invention of the first and the first demonstration of the quantum cascade lasers in 1994. And since then, he has received numerous awards. So with this, I would like to actually hand over the talk to you. And I'm happy or interested also to hear what you have to say.
Myself, thank you.
Yeah.
And welcome everyone. It's it's a great pleasure. I actually I see many names that I know, and well, I would welcome you very warmly to this presentation of today. So in a sense, the executive summary has been made. So you heard what great things you can do with a dual comb spectrometer. What I would like to spend a bit of time is now to tell a bit, what is behind, in a sense, how it works, why does it work, and what can we look forward to. So, of course, the first thing is, what is this optical frequency comb? Well, just think of it at this point as an optical source that generates equidistant optical modes, and that those modes are locked by nonlinear process. And what, of course, is the beauty of such a source is that it allows you to write this formula where you can basically write the frequency of any one of these lines as a function of just an integer, which is this n here, and a repetition frequency, which will then lie in the microwave. So in that sense, the beauty is if you're able to control what is called the offset frequency, meaning the frequency of the first line, even if it doesn't appear, of the comb, then you basically have, with just two numbers, you basically can fix this whole ladder of frequencies. This invention was, of course, a revolution, was one for which Ted Hench and Jim Hall got the Nobel Prize in 2005. Its most important application initially was from time and frequency metrology, but as we'll see, this actually has now also extremely strong implication for spectroscopy. Now, obviously, just to really nail the point down and insist on it, you could imagine generating a fancy array of lasers, and people have done that, where you actually you make a number n of distributed feedback lasers that would be tuned individually to a very specific frequency. That would not be a comb, and it would not be a comb because you would be lacking the correlation between the frequency of the modes. And the correlation of the frequency between the modes mean that now the noise in frequency, because you have, of course, in any real laser system, the frequency is never perfectly stable. You will always have a slight frequency jitter, and that frequency jitter in a comb is correlated. And it's correlated such that if you measure the difference of frequency between adjacent modes, you will find an error, you will find a jitter which is much smaller than the jitter of the mode themselves. So it allows to do this famous dual cone spectroscopy, which is at the heart of the instrument sold by IRsweep. And interestingly enough, was of course not invented by us by far. It was actually a development that predated a lot. It was actually developed in part by Fritz Geilmann and also some groups in the NIST. And it really based on the idea that if you take two of such frequency comb and you beat them onto a single detector, and you now choose those frequency comb to have repetition rates that are slightly different, then you can see that as a highly parallel heterodyne experiment. So each pair of line here will create a beat tone at a different frequency, and those frequency will be equally spaced because you start with two combs that have equally spaced frequencies. Now, of course, the next application of this for a spectroscopy is obvious. Imagine you actually introduce a molecule that absorbs some lines in the optical domain. Those lines will, of course, be mixed. When mixed in the detector, will have also lower intensities, and therefore you'll map, if you want, the spectroscopy, the spectrum in the optical domain onto the electrical one. And of course, that's beautiful because you can do that very fast. It looks a bit like a Fourier transform infrared spectrometer, but it actually has no moving part, and all the analysis is done electrically. So QCLs are good for generating optical frequency comb in the mid-infrared. Why so? Well, we realized a few years ago, indeed, and actually Andreas was the first author and the leader in that paper, that if you take a quantum cascade laser that operates in the mid-infrared and actually is broadband in its gain, you actually have naturally the device that tends to emit this very regular spectra, such a way that when you were to mix the modes together, you were to beat them onto a single detector, we could observe extremely narrow beat node. And the extremely narrow beat node really is this proof that the modes are locked together, because you would never get such a narrow beat node if the jitter of each mode would be independent. And in a sense, that experiment of just focusing your light of the laser onto a detector and measuring the RF spectrum is still at the heart the most simple, but also a good indicator whether your device is operating as a comb or not. And one feature that we also discovered was that the laser is its own very nice detector. So you don't even need an external detector because actually the very fast transport that you have into a quantum cascade laser uses inter-subband transitions in quantum wells, and as such has lifetimes that are sub-picosecond. And that means that if you want, the current is following very faithfully the intensity inside the cavity in such a way that it's really no problem for an RF beat tone at 10, 20, 30 gigahertz to actually be transduced into the feeding current of your device. So, you know, a QCL comb, it looks just like a little, this example here, a 6 millimeter long Fabry-Perot device just soldered onto a copper submount. Now, behind, if you go inside, why does it behave as a comb? Well, to have a comb, you basically need to start with a cavity that has modes that are pretty much equally spaced, such that you start with this thing that wants to have equally spaced mode. Then you need to provide gain such that you now generate light, so you amplify those modes. But of course, if you just had gain and nothing else, there's nothing that would force those modes to lock together. And what you need is a nonlinearity, a way of mixing a higher order process where, for example, you absorb two photons, re-emit two photons, such a way that in this four-wave mixing nonlinearity, the difference frequency between adjacent modes tend to be equal, regardless of the pair of modes that you choose. And that nonlinearity, of course, wants to create a comb. And the beauty of quantum cascade lasers is that both gain and nonlinearity are provided in the active region, again, because of this very fast upper slit lifetime and this very fast response of the active region. Now, if you design your device correctly and play a bit around, you can make devices that exhibit very nice performance. In that case, those are the example, unfortunately not so common, but let's say those are the example of those devices that operate with 100 inverse centimeter bandwidth, up to a watt of optical power, and show very nice, very sharp beat tones, such a way that over this, this bandwidth, you basically have more than 1 milliwatt per mode. Now, if you look at those, the quantum cascade laser, they are uniquely, I would claim they are uniquely suited to make dual cone spectrometer. And the reasons are, some are very simple. power is simple. The fact that you have 100 milliwatt to 1 watt of power, this is nice because it allows you to go through very thick, optically thick sample. It allows you to also waste power at different places to reduce the feedback effect. You can really manage a lot of things if you have power. One thing which I would like to discuss a bit more is this repetition rate. The repetition rate, the distance between modes in the frequency domain, is about 10 gigahertz. And we will see that has actually a very beneficial aspect. One feature that is very unique also, if you compare that to, for example, a fiber laser, is that it's easy to tune the device. You change the temperature, you change the current, and you can tune it relatively easily over its own repetition rate. So you can cover essentially the whole frequency range. You can tune it fast. As we said, the optical bandwidth remains okay, but it could be better, of course. Something about the control of the device and the stability I will discuss a bit later. But just the repetition rate. Why is the repetition rate such a nice thing? Well, it's because if you look again at this dual comb, you realize that, of course, what you're doing is you're compressing the optical spectrum onto the electrical domain. And now, obviously, since you want a one-to-one mapping, you will actually want to have you need to fit all the modes that you have in the optical domain into your RF bandwidth. Now, if you assume you have a half gigahertz of electrical bandwidth, it means that you can only have so much spacing between the modes. And that's why if you take a fiber laser that has a repetition rate of 100 megahertz and optical bandwidth of maybe 20 terahertz and 3 million lines, this spacing between the modes in the RF domain can only be of the order of 10 hertz. Whereas if you take a quantum cascade laser where you start with 10 gigahertz, you maybe have a bandwidth of 3 terahertz or so, you have much less lines. It means that it's easy, you can have 1, even 10 megahertz of spacing between the modes. And that means, of course, that you can now do your acquisition much faster. So this is really at the basis of the beautiful data that was shown by Andreas just before, where this dual comb, therefore, is a unique technique that allows you to acquire spectra, a full spectra, if you now push it to the limit, every inverse repetition difference in the repetition rate of your comb. That means spacing in your RF domain. And that is really something that you don't find in other systems. But it's actually, so you have this advantage of being very fast, but there is actually a further aspect to it. Is the fact that because you're fast, you can actually improve on the noise. And you have to remember that if you take a device, this device will have, in general, the noise on that device will follow a curve that more or less looks like that always. You have a technical noise, which will drop as 1 over f or 1 over f squared, depends. And then at some point, you will hit a fundamental noise, which will be a white noise. It is like shot noise. It can be shallow tones limit for the line width and so on. So what is very important is that by having this large repetition rate and being able to acquire the spectrum very fast, you can put yourself for one spectra into the nice place where you're only limited by quantum noise. And if you do that, you can co-add the spectra remaining in the quantum noise and never being bothered by the technical noise, which of course is not the case if you have this very small spacing in the RF domain, which forces you to have a very long acquisition time. Just as a reminder, if the surprising thing is that, well, the good and in a sense, really the proof that this device is a comb, those were measurements of the line width that were done in my group by Francesco Capelli back in the days, which showed that when the QCL operates as a comb, its optical line width is limited by the shallow tones, and it's limited by the shallow tones where the power is the power of the whole comb, not the power on one line. So it means that even if you have hundreds of lines and you're sharing 100 milliwatt of power over hundreds or 1,000 lines, each line will have a line width of the order of 100 hertz also. So that creates really a beautiful playground to do then high resolution spectroscopy. So the correlation between the lines allows you also to remove the technical noise when you do this long acquisition. And there I would like to cite the work. There was many different works that were made, but I would like to cite the one of David Bergerhoff, who basically showed that a few years ago now, using terahertz combs. He basically showed that since you know that the device that you're observing, the two combs that you're observing have only two possible sources of noise. One noise would be the offset frequency that is jittering. The other noise is the repetition rate that is filtering. And therefore, since you're acquiring hundreds of modes, but you know that there is only two parameters that will generate that noise, you can actually infer the noise from the measurement. And in that case, here is an example where they measured over a long time this dual comb spectra, and you don't see anything. When you looked at a very short time, you start to see the modes, of course, because there you don't have time to jitter too much. And they showed that by doing a Kalman filtering, nonlinear filtering, they could actually improve the signal of noise. Another example here is shown by the COCOA algorithm, as called by the group of Gerard Wieselke and Jerry Westberg. This is just a little animation and a movie of the data showing what happens if you simply co-add the spectra without doing correction, while if you do a correction, then you can actually preserve and improve on the signal of noise. That means you can stay in the blue part of the graph, whether when you're adding without correcting, you go in the red part and you're killed by the 1/f noise. So if you think a bit more and you ask yourself, okay, what is the limitation on the signal of a noise that you can have? Because in the end, if you're doing a absorption or spectroscopy measurement, this is the important number. And the amplitude signal of a noise on the detector for a single line, you can write it. It is, of course, inversely to the bandwidth because it's a heterodyne measurement. And what you see here is that it basically, of course, is proportional to the ratio. This is the power in the two beams, a local oscillator and the sensing beam. Now, what is important, of course, is that you pay a price for having 100 lines, is the fact that signal of a noise, if you want, is detrimentally goes like 1 over the n square, the square of, this is in that case the variance, the square of the number of lines that you have in your cascade laser. So, of course, the reason for that is because you have only one line that you're detecting, that you're interested in that case, but of course the detector sees the photocurrent from all possible lines at the same time. But the beautiful thing is that you can afford to have this parallelism. And the reason you can afford it is that most of the optical sensing systems are not limited by photon noise. Because if you have a decent detector and 1 milliwatt of power, you can show that you should get a signal of noise of a sensitivity in amplitude of something like 10 to the -8, which of course you can never achieve in an optical system. So in a sense, you're willing in a comb to sacrifice some signal of a noise over a single frequency sensor, but you sacrifice something that you cannot use anyway. And this we showed already years ago in this first paper where we showed this dual comb, the first dual comb spectroscopy experiments. We showed here that indeed, as we're integrating the noise, of course, we had at that time still technical noise that we did not know how to remove, but we could see that for relatively short times, you could be very close to the simulated photon noise, that we could be limited by the photon noise as in this spectroscopy. And that means in a way that you can really push this technique close to the fundamental limits. The other thing, which of course is very beneficial, is this tunability and the fact that you can tune fast. And there, obviously, you've seen the data. I just wanted to show a bit how that type of measurement were done. This is work that was done actually in the group of Lukas Emmenegger in EMPA. But the whole problem is the typical criticism that you get for people when you show and you say that you're going to work with a dual comb with a 10 gigahertz repetition rate, they're going to say, well, but you cannot measure a narrow line. Well, of course, if you have here as depicted a very, a spectrum that contains a very sharp absorption gas, absorption lines from a gas, because you have a low pressure gas in a cell, and you want to do very fine spectroscopy. Of course, if you just have one comb, you will absolutely miss sometime a line, or you don't have a faithful spectrum. What you have to remember is that you do the dual comb by having your local oscillator being slightly detuned, and that each pair of this mode will create your spectrum, will create, let's say, this line into your RF spectrum. Now, of course, what you can do is take advantage of the fact that you can tune both the local oscillator and the interrogating comb by just ramping the current. And I refer you to this publication for the details. And the idea is, well, if you can do that, what you can do is simply, you will slowly, you can slowly go over that line by simply tuning concurrently both the sample channel and the local oscillator channel, keeping the RF signal in the bandwidth of your detector. So in this way, you basically can do a slow scan compared to the speed at which you're acquiring each spectrum, but that slow scan remains still very fast on the scale of what you could do with a high resolution spectrometer. So, and the other thing that of course you still have is, it's not been implemented yet, but you can still in principle reference this comb electrically and optically, such that for each one of the spectra, you have an absolute measurement of all frequencies, in which case you really would have a completely frequency tagged spectrum with an incredible high resolution. So this is how the group of Lucas and Menegger obtained those beautiful spectra that you saw that were shown and that were published now in this paper. Where the impressive thing is that you can do this spectroscopy over a full 16 inverse centimeter of bandwidth, and with a very nice high resolution. But I understand that since then the group of Muriel Lapierre, they observe even better. But I think it just shows, this was really a first experiment, it just shows the potential for this high resolution spectrum. The last part of my presentation, I would like to dedicate to a bit more forward-looking. What can we do to, for example, improve the optical bandwidth, make those devices even more controllable, maybe improve on the stability, which are typically the thing that maybe have a problem. So first, I would like just to say one thing about the output of the laser, so of the comb. Obviously, as I said, the comb is completely determined by the fact that it has equally spaced optical frequencies. But now, of course, as you may realize, if you take the same optical spectrum but change the phases of the individual modes, you can go from something that would emit short pulses to something that emits almost a continuous intensity with no intensity modulation. And for a long time, it was relatively clear that the quantum cascade laser was operating more in that regime of this constant intensity, but it was not really clear if there was any rationale to the output. So there, to make a long story short, there were techniques of the ultra fast to try to solve that problem, but they were not really applicable so easily to quantum cascade lasers. And so the idea here was to actually use that beat note that I described before to infer the phases. And that actually was really nicely developed theoretically and also experimentally by David Burghoff. So here the idea is that you actually consider, if you consider every individual beatings between individual pairs of modes, those beatings will each create an RF beat tone that will have its own phase. So in a sense, the only trick is how can I selectively measure this phase difference by basically looking at the beating between each pair of modes. And you can do that by basically passing this the output of the QCL through a Fourier transform infrared spectrometer and making a current detection. So this is what you do, and it was done by my student Matt Singleton now a few years ago. And what was really surprising is that the phases, so this is the amplitude of the modes, and on the bottom you see the phases, and you see that the phases are actually almost perfectly quadratic. So what you're talking about in technical term, it's a highly chirped output. It chirped output, and it reflects the fact that the laser is actually chirping linearly with time. So its frequency increases linearly with time during a period and then resets. And now actually recently, the Berghoff put an archive that really shows it very beautifully why such a behavior can arise from a consideration of phase solitons. But just to prove in a sense that this output, if you want, is real, one thing that you can do is try to convert that, constant output into revert that, if you have an output that has a quadratic phase, a natural idea is, well, if I use an optical element that removes that phases, I should get pulses. And that's what we did here using this double grating for F system and analyzing again the signal. We showed that by moving that for F system and changing the dispersion, we could bring all this energy back and basically achieve a single pulse. And okay, that pulse is not very pure. It's not very pure because the phases are not exactly parabolic. They are approximately parabolic. So the other aspect, which is fascinating, and I mentioned it a few times, is the fact that you can see this quantum cascade laser as you have a cavity. The cavity creates, in that cavity, you have many modes. They interfere with each other. And those modes will actually, of course, the interference of those modes will create maxima and minima that can change with time. And since you have this very fast transport, the QCL actually detects itself, this current, in the RF. So you can see this also a bit as a Chi2 type of interaction. But now what you can do is invert the process, and that actually was done already when we actually first studied this device. And we showed already that at that time that you can actually, by injecting now, instead of extracting the RF, you just inject it, we can actually pull the center bit node of the device. As I said, we can extract. And actually in work that was done in collaboration with Carlos Sirtori's group, they showed actually that if you have in microstripped quantum cascade laser, you can actually lock this device over a much broader frequency range. Another development trying to stabilize the devices was a work where we actually used the so-called tapered waveguide. The idea is there are two contradictory features you would like out of your waveguide in such device. First of all, you would like that device to be very powerful, and you also want to have it very low dispersion. At the same time, and if you wanted high power and low dispersion, you would make a very broad waveguide. But at the same time, you want to make sure you have only one mode that survives, and also you want to make sure that you have a high intensity inside the waveguide. So we thought, well, maybe by combining those two features, we could get both high regions with very high intensity in the part where the waveguide is narrow, and at the same time, if you want an amplifier section, we get more gain. And sorry for the very bad quality. I did that a bit at the last minute. But what I plot here is the group velocity dispersion, indicating how much dispersion you have from the device. And you see that with this scheme, we can get a very flat group velocity dispersion. And as a result, yeah, I see that some slides are good, some are not. As a result, we get a very decent bandwidth, about 15 verse centimeter or so. But what is very important is now we see that the beat tone is very, very pure and also can be tuned over the whole temperature range and the whole current range, remaining very pure. You see that we have more than 40 dB of signal over noise and that the line width remains between 1100 and 1400 milliamps. The line width remains very narrow. And to finish, another interesting development, even more, it's more conceptual, if you want, than really at this point giving us the bandwidth, is the idea of using ring QCL combs. The idea here is that for those who are in the field, you know that spatial hole burning is seen as a very important contribution, element that generates, if you want, the locking of the mode. So the idea here, well, if you do a ring, you remove the spatial hole burning, and this was done using a technology, the buried heterostructure technology. And if you want, the answer is, on one side, is nice. The device works. It, at this point, had no extractor, so of course the power is ridiculous. Is only 80 microwatt, but that is just because we didn't have any feature to extract, so the light is completely trapped inside the ring. And the interesting aspect is that we indeed saw a comb. The bad news is that that comb is actually very narrow band, and in that sense also confirms the fact that somehow the spatial hole burning, or let's say the Fabry-Perot cavity, seems to be quite critical in getting very broad combs, at least for that type of intensity. And one interesting feature was that, contrary to what you could fear, that device operated, the mode was circulating only in one direction. And we could see that by a simple experiment. So we turned on the ring, and we basically could move the lens that was detecting the output. And you can see, if you want, the emission from that ring is a bit like what you get out of a synchrotron. It's the light that actually escapes through the, that it's really the bending loss, if you want. And now, of course, if you have a mode that run clockwise, you will see the light coming from that edge. Whereas if it's counterclockwise, you see it coming from the other edge. And you see here, this is a picture of the experiment, and this is a picture of the beam. And you see that the beam indeed has a bit what you would expect for shape from a light that just escapes from the, by basically tunneling through the bending losses. And so what really we could show was that the light would come from one side or the other, depending on how we would turn on and turn off the device. So as a result, the spectra that I showed here were really spectra where the device was operating only in one direction. And the nice aspect of that device is, of course, that it was extremely stable, and it could be, again, we could see a nice beat tone with a very narrow bandwidth over this complete current range. So that just, of course, spells it's at the same time it's very attractive. At the same time, it still remains a very narrow band. So you would need to combine that device with another, some other scheme to actually broaden further the output. So another interesting thing was that we could retrieve the shape of the output by doing again, one of this swift spectroscopy, by mixing, if you want, this ring comb with a Fabry-Perot comb, and doing a dual comb experiment and a swift experiment, and using this information, basically get the time profile of the output of the device, which actually was surprisingly intensity modulated. So it really shows that the ring have inherently a quite different operation mode as the Fabry-Perot ones. So what I hoped I showed you is that quantum cascade laser combs are uniquely fitted to do dual comb spectroscopy. They allow this very full spectrum acquisition. They are very powerful. They allow you to follow chemical dynamics in real time. And what I think extremely attractive is the possibility of creating extremely high resolution spectrometers in the mid-infrared, are completely referenced in frequency, and that have enormous resolution power. And I think there's actually some recent, very interesting work, a various theory group that start to understand how the quantum cascade laser comb really gets its comb characteristics. And I really hope that this will be really the essential element that will allow us also to make broader and more stable combs. With that, I thank you for your attention. And I see there are a number of questions I will try to answer.
Thank you, Jérôme, for this excellent talk. Yes, we actually get now to the Q&A session. I think maybe it's better if you keep your presentation open, because it could be that we need to go in some technical details. So the first question was an expected one. So we have now 60 to 100 wave numbers about. What do you think in terms of coverage can we expect in the near future? I mean, we know that QCLs have a broader bandwidth.
Yeah, I think it is really, if you want, it's hard to really know for sure when that will happen. In a sense, I'm really quite hopeful, because we know for years that you can make the quantum cascade laser that emits over 250 inverse centimeter continuous spectrum. It's not locked. And I think this new work by the group of Berghoff, by also other groups, really, I think, point probably to the techniques that you have to put together to make this locked over this broad bandwidth. I think it's really a question, it's not an easy question. I think it's one of those problems where you have to put different things together. And that's why I see ourselves still in the mode where you understand parts, and at some point you'll be able to put all those parts together, and suddenly you'll get back this 200 inverse centimeter that you need. But I'm quite sure it will also need quite some, some optimization on the technology side.
Yeah, I agree with you. But of course, if we can reach 200, 250 wave numbers, that would be, I think, would be really
that'd be my goal, absolutely.
Yeah. So we have a question from Jürgen Söchtig. Maybe that's a bit more addressed to my part of the talk. You use separate QCLs to cover a broad spectral range. Can you get similar results with near-infrared or mid-infrared tunable laser sources? As an example, he gives OPOs, or is their bandwidth too large? The short answer is that you cannot get similar results, and it depends always on the application or on the experiment you're doing. But since the QCL COM, you actually probe everything in parallel, so it allows you to basically have an enormously fast resolution of or basically recover your spectra within 250 nanoseconds. That's basically the limit that depending on the repetition rate, what Jérôme was explaining. So if you want to get such fast high resolution spectra, a tunable source will not do it for you, and you will not get the same results. Then the next question is by Sheng Wu. Is the ultimate detectable absorption noise determined by the power on each line?
Yes, I would say so. I think it's really, well, you, of course, with the caveat that detectors have finite saturation powers. Yeah. So you cannot put an infinite amount of power onto your detector and hope that you will gain on signal noise. But otherwise, I think, the instruments are photon noise limited.
Yeah, I agree with this. We see actually that lines with more power have a better signal to noise ratio than lines with less power. And then depending on how long you integrate, you, of course, then at a certain point, you hit another limit in your system. But overall, I agree. So there's a question from Konstantin Vodopayanov. How do you reference your absolute frequency, and how do you get 10 to the power of -5 wave number spectral resolution with mode spacing of 10 gigahertz? So maybe I have to clarify here. I try to be very clear what I say. So I said we have an absolute frequency axis, an accurate frequency axis. And basically what we're doing is we tune the comb. And by the dual comb technique, what we can do, we can basically tune first the first comb, then the second, and the third, and then use the heterodyne signal as a ruler to get an accurate frequency axis. So the point spacing are actually measured using the dual comb, but then the absolute spectrum has still an uncertainty. For the research for Muriel Lepere, for example, where they want to measure line shapes, that is perfectly adequate. But then if you want to have an absolute frequency, I think then you have to go to other locking techniques that Jérôme was referring to. And the other question about spectral resolution, there it is a bit it's a very tricky question, because basically the spectral resolution is defined as being able to define two neighboring points. No, that if you have 2 points in your spectrum, and can you actually measure a feature difference? And the fact that the laser from, or the solution from Lukas Emmenecker, where we tune the laser very fast, actually helps to improve the resolution and be able to distinguish 2 points. But you still sacrifice in your absolute spectrum on the lower end. Nevertheless, you will be able to distinguish very narrow features, but you will have a distortion. So I think it is a very tricky question. What is the resolution? What is the absolute frequency?
If I may add, I mean, thanks for tuning in, Constantin. You see, what you have to realize is when you do spectroscopy with a distributed feedback laser, what you do is you do a ramp in current, and you actually assign for each current the frequency, and that works well. And you need to calibrate it once, and then you usually almost assume that device, you basically have, it's not an absolute frequency, but it's actually given by the tuning of the device. But since the device is very stable, it actually provides a good frequency axis. Now, of course, the comb in that sense works pretty much in a similar way. So that we've observed, it looks like it's maybe not as good as a DFB, but it also has a very predictable, except if you have jumps, it has a very predictable change in frequency as function of current. So of course, if you want to do things proper, you would have to reference one line of the comb to a stabilized laser, for example. That could be one way. There are many ways of doing that. So you could, of course, implement absolute frequency reference, but still the point is that even if you don't have it, you're actually quite accurate.
Yeah, I agree. Question from Pete Bowden. Hi, Pete. So it is about the measurements in Boulder. The question is if they were performed in the solid state or in solution, and if the sample was exchanged after each laser shot. So it was in a solid state, and we had 200 shots, and it was not exchanged. Then the next question is from Farid Khan. Can you please explain a little bit about the technical noise if we go lower in the repetition rate? Then you meant technical noise will be more dominated. If yes, then what would you suggest to tackle this as 10 gigahertz is too higher? Move towards CW-based comms?
Well, I mean, so the point I just want to make is technical noise is, for example, temperature fluctuations, or the device drifts. So the reason I remained a bit vague is because, of course, if I wanted to be more accurate, I would have to define: am I talking about the amplitude? Am I talking about the device? Am I talking about and so every feature will have a bit of a different behavior, but the general idea is the following: if you measure a very small signal and you just to plug if you just measure that small signal and do not have a reference, at some point you don't know what you're measuring, because you don't know whether you're measuring a drift due to some parameter changing, or if you're measuring really your signal. So that's why you use a lock-in. You basically periodically stop your signal and you measure the difference with effect or without. And basically what we're doing here is the same. What we're doing is we're doing an acquisition fast, and then we always compare to no acquisition, if you want. And that is in a way, by acquiring fast, you actually move away from this drift. So you make sure that during one acquisition, you have as little drift as possible. That's the idea.
Yeah. Thank you. Question by Muriel. Taking into account the limits of QCLs, what are the spectral domains we can expect to reach in the future?
Well, I think there, I would say anywhere between probably 3 micron to 11 micron. I mean, in a sense that I know that interband cascade laser also have shown comb operation, and it's not clear. I mean, I would also suspect QCLs in the 3.5, 3.8 micron probably could also generate combs. So it's a question of, you know, at this point, the time for developing all those sources.
Yeah. The next question by Alexander Ebner is basically asking if the spectral limits of basically the dual comb spectrometer, if the bandwidth that we cover there is limited by the QCL chips, and then the question about the future on the bandwidth, which we already answered. Fundamentally, the limits are given by the QCL chip bandwidth. So if we have broader chips, we will have a broader dual comb spectrometer as well. Then the question about in experimental applications, do you have problems because of intra-cavity absorption of atmospheric components?
Depends on the wavelength, of course. You need to purge your instrument probably if you're working in the water band. Yeah, this is like any spectroscopy in the infrared will have this same.
Yeah. Well, one thing is actually the nice thing. So at 1650, where we have the biospectroscopy, you have a lot of water lines, but there the broad bandwidth really helps you because you can always basically treat water as a component that you want to measure in your matrix. So I would say it's actually a solution to the problem than the other way around. Can you also do the calibration with a natural constant such as water vapor, where the lines are well known?
Yeah, I guess this is a trick also. Spectroscopists, I know that a number of instruments, they use lines outside of the one they want to measure that they know are going to be there to calibrate their frequency.
Yeah, exactly. So basically, if you have water lines, you know where you are, and then you have an absolute frequency by measuring it. Do you see any possible spectroscopy applications for very high rep rate QCL comms, for instance, 50 gigahertz QCL?
Well, I would say so, yes. I think if you want to do a very fast dual comb, you probably will want to have a very few lines and therefore use very high repetition rate QCLs.
Yeah.
Then you could, in principle, have extremely fast acquisition. Of course, a very few spectral points, but maybe that's the one thing you would want to have, depending on the application.
Yeah, I agree. If you have a very broadband absorbers, maybe actually you want to have power in less lines.
Exactly.
Yeah. Then can COM be used in mid-infrared radiometry?
That's a very interesting question. Did we ever try to measure a black body with a dual? I mean, in that sense, it's just a single comb. It's probably a signal of noise, which is tough to achieve. Because what you have to remember is, of course, you're doing more or less a single mode detector. So there's not much light inside. Well, by definition, you have a single mode detector because you're doing a heterodyne with a coherent source. So since you have a single mode detector, it means that the amount of energy you get from an incoherent source is very small. But maybe, I don't know, maybe it's a very interesting suggestion.
Yeah, it is an interesting suggestion, and I do know people who work on some aspects of that. But I'm bound to an NDA, so I cannot say much. But there is for sure work being done in this direction. Yes, I think with this we have covered. There is there's another thank you. That is always good.
Yeah.
It was fantastic, Jérôme. Thank you for
thank you
being
for the
part
invitation and
me.
the opportunity to see a few people. At least I didn't see them, but I mean, I sort of had them on the audience.
Let me quickly take the control back. So this was the question and answer slides. So I would like to basically point out that the webinars, we have a very active webinar culture. We have many of our customers, Ian Burgess and also Nicholas Binkowski from Hansen Group, for example, who gave webinars, and we put them online, so you can also watch them afterwards. So please have a look at them if you see anything interesting, and contact us if you see any applications which would be interesting to basically attack with the IRsF1. With this, I would like to conclude this webinar and thank Jérôme once more. And
thank you, Andreas.
So see you soon. Bye.